And next is our very awesome speaker that I'm very excited to introduce to you all, Dr. Kiri Nichol. Kiri is a data scientist, a machine learning engineer, and a researcher. She got a PhD in physics and afterward did her postdoctoral work in medical imaging, after which she delved quickly into machine learning by way of solving complicated problems on Kaggle. Kiri's current research interests include using unsupervised methods to reduce the amount of labeled data needed for deep learning. And fun fact about Kiri, in 2013, she was a finalist in setup.nl's competition, challenging you to create an algorithm to fake a Mondrian painting. And there was a film clip of her algorithm exhibited in the Gemeentemuseum in The Hague. Kiri.
You can take it here. All right, so my talk's actually in two parts. The first part, I'm going to talk about a Kaggle competition that I organized. And the second part, I'm going to talk about what I like about Kaggle, what I'd like to tweak about Kaggle, and what I kind of imagine for machine learning in the next 5 years. So here is an interesting question. Are these two paintings by the same artist? So of course, if you're a human being looking at this problem, you might look at features on a large scale, like is perspective rendered in a realistic way, or what's the color palette like? Or you might zoom in a little bit and you might look at the people in the image and how are they dressed? And you might also zoom in a little bit further and look at things like how is lace rendered, or what are the brush strokes like? So of course, the reason that we're all here is that we're not really interested in how humans solve this problem, but we're interested in can we get the machine to solve this problem? And I feel optimistic that with this audience, this slide is probably all review. So I think what I want to say about it is that convolutional neural networks are really amazing. But of course, they could be a bit better. So I started thinking about this competition in 2015. And the state of the art then was to take an image and reduce it to 224 pixels by 224 pixels. If it wasn't square, you would just pad it with zeros. And you would show this to your algorithm. And what I really hope by encouraging people to think about this problem was that they would be able to come up with some methods for dealing with different sized images. And I think this is really well illustrated by the cover of my favorite book about machine learning, Galatea 2.2. So the other problem that existed in 2015 was that you had to resize your image so that it was really tiny, and you basically had no way of retaining any very detailed information. And so what I hoped by working with this data set was that people would be motivated to develop some sort of attentional mechanism. And I think actually that this is something that people are still working on. So for instance, if you go to Keras today and download a pre-trained convolutional neural network, you don't have something that has an attentional mechanism built in. And I feel kind of surprised about that. And I think maybe one of the reasons that we don't actually have an attentional pre-trained neural network is that the kinds of data that we train on are usually like fairly tight photos of like the CIFAR image set. And art is really interesting because there's information at different length scales. And I think that this is an interesting data set that might motivate having an attentional model in Keras. So the problem of identifying who painted a painting is a form of supervised learning. And the way that we normally think about supervised learning, we have a painting, we show it to the algorithm, and the algorithm predicts, is this painting by Vermeer? Is this painting by Da Vinci? Is this painting by Van Gogh? And there's another way to think about this, to make this a supervised problem, and that's by using a Siamese neural network. So actually, I'm curious, who here has trained a Siamese neural network? Okay, good. Then you're all going to learn something. So the idea with the Siamese neural network is you have an image on the left and an image on the right, and you show the algorithm that same image on the left and the same image on the right, but it's the same weights in both the left and the right algorithm. You're actually just duplicating the weights. And you take the output from the image on the left and the output from the image on the right, and then you glue them together in some way where you're making a binary prediction, and that prediction is, are these two paintings by the same artist? And the really nice thing about setting up this problem this way is that you can have artists who don't have work in the training set and have work in the test set, and now your algorithm can learn how to extrapolate to artists whose work it's never seen before. So to do this problem, I had to get some data. So I went to wikiart.org. They have about 150,000 paintings and a lot of metadata, who painted the painting, what sort of style the painting is. And I sent them a little email, and I said, hey, would it be OK if I scraped your website? And they wrote back to me, and they said, Yeah, maybe keep it to one painting every 10 seconds. So the moral of the story is call before you scrape, because sometimes they say yes. Anyway, so I wrote my scraper. It failed a couple times, but after about 3 weeks, I had 150,000 paintings sitting on my hard drive. And at that point, I actually approached Wendy Can and asked, hey, could I run a Kaggle competition for you guys? And she said, yeah, OK. So instead of keeping the problem to myself, I decided to share it with all of you. Now, there are a few things that I had to think about carefully when I was setting the problem up. So the test data set had about 20,000 images. And if you ask people to compare every painting in the test set to every other painting in the test set, that's like 1 billion comparisons. And the submission file was going to be more than a gig, and it was just going to take forever. So I realized I needed a clever way to reduce the number of comparisons that I could ask people to make. But at the same time, I realized that I needed to be really careful about doing this. And the problem is that when you have, most comparisons are actually, these two paintings are not by the same artist. And what I've done here is I've plotted, I've just picked 100 paintings by I think about 8 different artists, and every time painting I and painting J are by the same artist, there's a red dot, and every time the two paintings are by different artists, there's a blue dot. So of course the diagonal is all red. And the problem is that if you just randomly sample, say, an equal number of situations where the paintings are not by the same artist relative to the paintings that are by the same artist, what you end up doing is you're giving people information. And people will go in and look for triplets of paintings where if you ask somebody to compare painting A to painting B and painting B to painting C and also painting A to painting C, what you've just told them is these 3 paintings are actually probably by the same artist. So you don't want to do that. And so I needed to come up with a way to reduce the number of comparisons without giving this information to people. So what I did was I went in and I used the style information that I'd scraped off of WikiArt. And so this was things like, is this painting an abstract painting? Is this painting a realist painting? Is this painting a pointillist painting? And I constructed a vector for each artist. And then to make this plot, I just took the dot product of every artist vector with every other artist vector. So when you see a dot that's blue, that means these 2 artist styles are very dissimilar. And if you see a red dot, that means that these 2 artist styles are quite similar. So this is a very nice plaid pattern, but I needed to pretty it up. So I used Cut-Hill-McKee ordering from NetworkX. And what this has done is it's grouped similar artists. So there's a chunk of artists, I think between about 600 and 800 that are, I think that's Renaissance painters. And then there's a small group of artists that are like Japanese from the 1700s, which don't look like anybody else. So they form a cluster that's not related to other artist styles. So once I'd been able to group artists this way, what I did was I broke the test set into 13 sets of artists. And for every painting in the test set, in each of these groups, I compared all the paintings for each artist in a particular group to all the other paintings by an artist in that group. And there are actually a few artists that had a really huge number of paintings, and like Van Gogh, for instance, has a huge number of paintings. And so I was able to put Van Gogh paintings in every single one of the 13 groups that I broke the test set up into. Let's see. All right. So one other thing I thought about in this competition was cheating. So I'm fairly confident that nobody here recognizes this painting because it's by somebody I know who lives in Edmonton. She paints the Northern Lights. That's her portfolio. So what I did was I went and found a bunch of undiscovered artists and put their work into the test data set. So anybody who would be motivated to cheat by scraping WikiArt or doing a reverse Google image search would find that they were probably wasting their time because there was a lot of paintings that they just could not find. The other thing I did before I got the competition going was to make a really dumb benchmark. And I actually just threw out everything about convolutional neural networks, and I just used RandomForestClassifier. And I made 2 really dumb features. One is just the aspect ratio of the paintings. And the other feature was the number of bits in the image in JPEG format divided by the area of the image in pixels. So if you think about the number of bits in a JPEG image, what this is actually telling you is it's telling you something about the amount of information in the image. So if you have an image that's like all black, you don't need a lot of information to encode this picture. But if you have an image with lots of details and lots of variation, then you need a lot more. Your JPEG image is much larger. So the number of bits per square pixel actually tells you something about the information density of the image. So I made my little random forest classifier benchmark and started the competition running, and random forest classifier came 16th in a field of 50. So I think the main thing I learned from this was that if you want to get lots of people in a Kaggle competition, you need to probably throw money at them, definitely throw Kaggle points at them. And if people need to use a GPU and the data set is really large, that's also a high barrier to people participating. So the metric for the competition is the area under the curve. So if you're just randomly guessing, the AUC is 0.5. And if your algorithm can perfectly distinguish these two paintings are by the same artist from these two paintings are not by the same artist, then your AUC goes to 1. The competition was won by a master's student in Slovenia, Nate Zelenic. And I'm actually going to talk a little bit about the results from his algorithm. I'm not going to go into all the details about how his algorithm works, but I would encourage you to look at what he wrote about it on the Kaggle message board. So the other thing I did when I set the competition up was I actually snuck some forgeries into the test data set. So this is Han van Meegeren. He was a Dutch painter who was active in the years just after World War I to just after World War II. And he had some modest commercial success in the Netherlands, but he felt like he was not being properly respected by the critics. And he thought he would flip the critics a giant bird by painting some forgeries of Dutch paintings from the Golden Age, from the 1700s. So of these 6 paintings here, 4 are by Vermeer and 2 are by van Meegeren. So what I've done is I've made a plot here comparing Vermeer paintings to van Meegeren paintings, and this is with Nate's algorithm. So anytime you see a red square, that means the algorithm thinks these 2 paintings are similar, and a blue square, the algorithm thinks these are less similar. So right away, what you can see is in the Vermeer corner, which is the bottom left, that there's a lot more warmer colors, and that suggests that his algorithm thinks that the Vermeer paintings are sort of similar to each other. Now, van Meegeren painted in many different styles, so you would expect that you would see less internal consistency there. There are also a couple of paintings that van Meegeren did that Nate's algorithm really thought looked like Vermeer's. So there's this painting of the woman by the piano with the man, and Nate's algorithm really thought that that had Vermeer-like attributes. And then there's also this painting that van Meegeren did of Jesus with the disciples. And man, his algorithm really thought that this looked like Vermeer's painting of this man standing by the window with the map. Vermeer painted a lot of paintings where there was a window on the left with light coming in. And so it's sort of understandable that this would be a painting that would fool his algorithm. So the final thing that I did when I set the test setup was I made about 5% of the artists not have any work in the training set. So now I can ask the question, how well is the algorithm able to extrapolate to artists that it's never seen before? So in the situations where you're doing a comparison where both artists have work in the training set, the AUC was 0.94, and in the case where neither artist has work in the training set, then the AUC is 0.82. And if I was a better person, there would not be 5 random digits of precision, and I would have bootstrapped error bars onto these values. So what I want you to take away from the first half of the talk is that Siamese neural networks are a really nifty way to train a supervised algorithm that can extrapolate to novel classes. Also, if you want people to participate in your Kaggle competition, you better make sure that you're dangling some cash in front of them. Kaggle points are also a really good idea. Actually, I wonder, what if you were to try to find a conversion rate between Kaggle points to money, what that conversion rate would look like. And also, if you have a really large data set and people need to GPU to participate, that's also going to drive down participation. I'm really gratified that somebody used this data set in a publication, and I realized if I don't come and tell people that this data set exists, then people won't use it. So here I am telling you all about it. And the final thought I'd like to leave you with is that we should think about how the data sets that we use are influencing the kinds of algorithms that we end up with. So the fact that the art data set is sort of very detailed, but also has information at different length scales, I think might be important for encouraging the development of an attentional network. All right, so the second half of the talk, I want to go over what I like about Kaggle, what I'd like to tweak about Kaggle, and what I see for machine learning in the future. So I really love Kaggle, and I think Kaggle is a good way to learn. And I use it as a kind of a form of cross-training, because if you want to get good at speed skating, then maybe you spend your summer riding your bicycle. I think being exposed to different problems helps train me to be more creative. I also think that like textbooks and courses just can't keep up with advancements in machine learning. And reading Kaggle message boards is just, it's like having the world's best textbook. And you get with all these up-to-date, incredible ideas that people are taking from literature, inventing themselves, and then executing in a competition. I also think that one of the reasons Kaggle is so useful is that I learn better when I'm actively engaged in solving the problem myself. Not only from what I try, but once I've tried to solve the problem, I'm in a better situation where I can see what somebody else has done, why it's clever. And I think that's really powerful and kind of underestimated. I would really like to see Kaggle be used more for research. And the main reason is it's relatively meritocratic. And well, anybody participating in Kaggle has already benefited. You probably speak pretty good English. You probably went somewhere you had a good primary education. You probably don't have a giant student loan debt that you're trying to pay off. And you also have lots of free time that you don't need to spend on things like taking care of your parents or taking care of your children. So it's a relative meritocracy, but it's also true that when you're looking at the Kaggle leaderboard, nobody cares where you went to university. Nobody cares whether your university is posh. And I really, really like that. I also really like that it's easy to see when one strategy is an improvement over another. And this is important in medical and engineering problems when you have like two different groups and they go in and they collect different data sets. And then it's kind of clear that they're solving a similar problem, but maybe it's not quite the same problem. And you can't really tell whether what somebody did in this group is an improvement over what somebody did in another group. And I think that having this, people get together and work to prepare a data set and then a whole bunch of people work on it, I think that's a really powerful way to do research. Of course, Kaggle is never going to give you things like leaky ReLU, for instance. A lot of the really fundamental things, I think it's just, you have to go in there and look at the machine learning literature and have some ideas about how you might improve this. But what I think Kaggle will also help to do is to introduce people to new data, new problems. So having come from a research background, one of the biggest problems that I had was actually finding a good research problem to work on. And Kaggle basically just like, here's a whole bunch of problems, go to town. And there's really two ways of doing research. One where you go in and you look at a paper and you're like, oh, you know, I have a better idea that I could use to improve on this, and then you go off and you try to improve on it. Or you go looking for doors somewhere that nobody else is looking at, and you open those doors. And looking at data or looking at problems that other people aren't looking at, I think is a key to doing really creative research. One other thing I really like about Kaggle is the discussion board. I learned so much from the discussion board. It's really civil. It's one of the more civil places on the internet. So thanks to all of you for keeping it that way. And I also think that the way that the message board is structured, it encourages people to write really straightforward and understandable prose. And it's also really easy to see, like, maybe you read something and you're like, well, I'm not really sure I understood that. But then you come back 3 days later and there's 100 people going, this is a good idea. And then you're like, okay, maybe I should go back there and try to work through that paragraph again. And I think, yeah, like reading a paper, that's all well and good, but having this sort of, the message board forces you to write very succinct prose. The other thing I like about Kaggle is that Kagglers frequently identify leaks or problems with the competition design that would probably go unnoticed in traditional read-only peer review. And like, I've actually really got it to hand it to the people who work for Kaggle. Actually, is anybody here who works for Kaggle right now who does competition stuff? Okay, well, if you see any of them, you should give them a hand and tell them thank you for all your hard work, because I think it goes underappreciated a little bit when people who win get all the glory, but it's really the people at Kaggle who are doing a lot of work to set this competition up and design a problem that makes sense. So what I don't like so much about Kaggle, like I don't like this particular board game here. In a competition with 1,000 entrants, or more than 1,000 entrants, winning is a bit random. Well, what to do about that? Well, just run more competitions. Great, fewer people per competition. Another idea would be to bootstrap error bars on the competition's rankings. And I think this would also be helpful for the companies running the competitions because it's useful. Somebody's going to win, but it's useful to know whether first place is actually a distinguishable improvement from 25th place. And I'm not going to go so far as to recommend how to calculate Kaggle points with bootstrapped rankings, but I did want to put it on the table as an option. So I'm a big ideas person, and I actually find things like ensembling and stacking really boring. And I'm trying to think of ways to structure competitions so that it's more of an emphasis on ideas and less of an emphasis on like parameter tuning and having zillions of models that you ensemble. And I think it's not trivial to think about this, but if there's a way to figure out how to penalize accuracy relative to the model size and the runtime, I think that would promote people to work on elegant algorithms rather than high accuracy algorithms. I also think that if I had a giant sack of money to throw around, I would do something like sponsor a Kaggle triathlon, where the idea is you write like one algorithm and then you try to win 3 competitions with that algorithm, or just do really well at 3 competitions with that algorithm without doing any manual feature building per competition. And I think that would help sort of to nudge along some of the some of the deep learning tools, because right now XGBoost and manual feature building sort of dominate, but I think it's definitely the case that there's some interesting ideas in deep learning that just aren't quite there yet, but having a prize might motivate people to work on that problem. So with Kaggle, the hard parts of doing machine learning are done for you. Somebody's collected the data, somebody's labeled the data, somebody's formulated the problem, and somebody's decided on how you're going to evaluate your predictions. And I put labeling a data in bold because I think this is actually, for companies and industry, their biggest problem using machine learning is actually to get labeled data. And typically what they do is they go and hire people like on Mechanical Turk, and this is expensive, slow, and it creates really shitty jobs. So I've actually gotten really interested in the last little while in using unsupervised techniques, and I hope that will help cut down on the amount of labeled data that we need to make deep learning work. Kaggle could also potentially run a competition with partially labeled training data. And what this would do is that it would really encourage people to develop techniques for doing unsupervised learning. OK, here's the other big thing about Kaggle. Unfortunately, for most people, having a real job is going to pay you more money than being a professional Kaggler. And I sometimes think about this. If I just didn't have a job in Kaggle for 2 years, would I make enough money at it that I could do it as my job? But it's hard to sort of it's not a reliable source of income, and I don't know. I also actually just enjoy working at companies too. And I'm also sure that if there was a business reason why if Kaggle could make money and pay people to do Kaggle, they probably would be doing it already. All right, so I've talked a little bit about what I like about Kaggle and what I'd like to tweak about Kaggle, and now I'd like to think a little bit about what machine learning is going to look like in the future. So the Orville is a science fiction program which is set 400 years in the future on a spaceship. And if I was a writer on the Orville, I would want to address things like, if Earth has self-driving cars in 2019, why are they still driving spaceships by hand in 400 years in the future? And I believe that the solution to this paradox is just that self-driving spaceships are super boring TV. So now that I've told you that science fiction gets things wrong about machine learning, I'd like to tell you about something I got wrong about machine learning in the future. So I'd like to travel back to June of 2014 when I was working on a Kaggle problem to identify when epilepsy patients were about to have a seizure. And so the data consisted of signals from electrodes in people and actually canine patients' brains. So you just got squiggle, squiggle, squiggle out of these 16 electrodes, and you had to make a prediction. Is this patient in a pre-seizure state? Are they having a seizure, or are they not having a seizure? And I looked at this problem, and I thought about Fourier transforming and doing all this fancy signal processing. And then actually I did something really, really stupid, which is I went to a pre-trained convolutional neural network from Café, because that was what we had in 2014. And this algorithm was trained on pictures of cats and dogs and chairs and peanuts and trees and whatnot, all photo images. And anyway, I took the squiggle, squiggle, squiggle from the electrodes in people's brains, and I just turned that into a literal picture. And then I showed that picture to this pre-trained neural network, and this pre-trained neural network came, I think, about in the top 25, maybe 20% of people. And so it wasn't a winning idea, but the powerful thing that this impressed on me was that machine learning could do feature building. And I looked at this and said, yeah, crap. Machines are going to be much better at feature building than I'm ever going to be. And I realized that from now on, I wanted to be using Kaggle as a way to train myself. I didn't want to use Kaggle to do XGBoost and manual feature building. I should use Kaggle to train myself to train deep learning tools to do feature building for me. So I've mostly focused on the deep learning side of things since then. Okay, of course, it's 2019, and people are still winning competitions with XGBoost. So how was I so wrong? Well, one thing I think is that fewer parameters in boosted trees means it's just harder to overfit. Another thing is that maybe that deep learning just conveys less of an advantage when you have lots of labeled data. And I think actually the biggest thing is that there's not pre-trained neural networks for doing a lot of competitions where you have some structured tabular data or some event-based data, which you have to do feature building with the event data. So where people win competitions in Kaggle with deep learning is it's all with text or with images. And those are problems where we actually have lots of good pre-trained tools. However, I'm going to double down on my prediction that deep learning is going to clobber XGBoost. And the reasons for that are that deep learning can model missing data. Deep learning can do feature building. I think deep learning can also learn how to combine data sources. And I already know, because I've made this work, that deep learning can be used to split data into maximally disparate CV folds. So I want to actually dig in a little bit more to what I mean by doing feature building and combining data sources. So typically when you, the sort of simplest Kaggle competition you can do, you get handed some sort of CSV file, and it's got a row with some sort of ID, and then the target, and a bunch of features. And I'm actually going to, for a concrete example, I'm going to use the Facebook fraud detection problem. So you have a target, is this bidder fraudulent or not? And then you have a whole bunch of features. And typically, what happens if Kaggle just gives you primary data, there's usually some additional feature building that you do, or there could be complications, like there's a really large number of features relative to the number of items, or you have lots of missing data. Or you could also have, they give you additional information, like events, and then you have to turn these events into features. So in the case of the fraud detection problem, you're looking at bidding activity in an auction, and so you have things like the bidder ID, the time that the person bid in the auction, and the auction ID that they're bidding in. And you have to come up with features like minimum time between bids. So if you have a bot bidding, maybe there's a really short amount of time between bids. Or the time between when a user bids and when the previous person bid in the auction. So when I work on this problem, I have to go through this event structure, and I have to come up with features like these, which I then plow back into the primary data, which I use to make the predictions. So what I think actually could happen is that we could make a pre-trained neural network for doing feature building for these sorts of event-based problems. So basically, I can imagine taking all the event-based problems that Kaggle has run and training a neural network to do the process of feature building on that. So that could include things like it does the Fourier transform, it calculates the standard deviation of the signal, and maybe there's other things that the algorithm will learn that we don't even know about right now. And so that makes the Kaggle competitions now look a lot more like, hey, want to work on this interesting problem? And then, OK, I'll go download the latest pre-trained model. Well, so this has made me think a little bit about what does it mean to be creative in a technical field. And I think one of the reasons that I'm creative is I've actually worked on problems in lots of different domains. So for instance, because of my background in statistical physics, I've had a lot of success building features that are based on information theory measures. But I can also, so the idea is that you work on a problem in one domain, you learn a tool, and then you go work on a problem in a completely unrelated domain, and you take your tools with you. Of course, the problem with having an algorithm do this is that they're going to be way better at it than I'm going to be, and I'm a little scared for that. So what does that actually leave humans to do? And I think the answer is to ask questions. So I have some competition ideas that I'd like to share with you guys. As you may have guessed, I'd love to see a competition with lots of, with partially labeled training data. I'd also love for there to be a kernel competition where people don't actually have direct access to the data. So here are the ideas that you can run some sort of aggregation operation. Like you could say, give me the average of values in this column. The Kaggle provides a generator, you provide Kaggle with a model. The Kaggle runs the model on the item served up by the generator and then just gives you the result. And what this is doing is it's actually a way to anonymize data. And I think for hospitals or an organization that would like to be able to keep their data anonymized, that having some sort of tool which allows people to run operations on that data without exposing individual information, I think that would be really powerful. And I think it would certainly make deep learning much more attractive and safe for organizations like hospitals to use. I'd also, because of my background in radiation therapy and imaging, I would also really love for there to be a competition doing treatment planning for radiation therapy. So in radiation therapy, the problem is you have somebody with a cancerous tumor, and you have a machine that can rotate around the patient and emit radiation. And you want to run this machine in such a way that you maximize the dose to the tumor, but minimize the dose of radiation to the healthy tissue. And I kind of wonder if there's maybe might be at the heart. It's an optimization problem, but there may be some advantages to using machine learning to try to solve this problem, or at least to speed up the dose planning process. Okay, even more competition ideas. I would love for Kaggle to be able to run reinforcement learning competitions. And basically any board game you can think of, I think, is a fair bet. I really like Dixit, Sushi Go Party, and Codenames, because these games actually, they have kind of nebulous goals. And they're also, certainly Dixit and Codenames are super visual. And I think they're hard problems in a way that are really unlike the typical tasks we ask convolutional neural networks to do. And I think that they're probably going to be something that's really difficult for people to make a lot of progress at. I also already asked Cards Against Humanity to share their data, and they sent me literally this meme. So sometimes asking nicely for data doesn't work out. I'd like to make a financial disclosure. My airfare and my accommodations are being paid while I'm here, but I'm not being paid for my time. And also, all the time that I spent on the Painter by Numbers competition, that was largely unpaid. I did use some of my 20% time in my job to work on the competition. When I'm working, I typically ask for a 4-day week, and then I use the 5th day to continue training myself. I'm basically my own teacher. And what this looks like is usually some combination of reading the Kaggle message board, doing Kaggle problems, reading papers, going to meetups, talking to people, and maybe doing my laundry as well. And I do this because I lived for several years in the Netherlands, and actually it's quite common for people there to work a 4-day week. And typically people would take care of their children or take care of an elderly parent, but people also use it to run little hobby jobs that wouldn't pay their bills if that was all they did, or to explore starting a business. And I really like this idea of the 4-day week. Also, I think anybody who's working as a data scientist or a machine learning engineer, you probably can afford to work less. And I also really think it's important to make an investment in being able to stay in tech and have a sort of durable career. And to do that, I really think you have to keep training yourself. So I know this is probably not an option for everybody in the room, but I at least wanted to sort of float that out there so that you know that it's on the menu. All right, I have a small advertisement. This is a plot of the labor costs for software engineers on the vertical axis versus labor quality in mysterious units on the horizontal axis. So of course, if you look for San Francisco and Seattle, they're in the top right, expensive but high quality corner of the plot. But it's really interesting to look at the 4 points at the bottom of the plot. There's Montreal, Ottawa, Toronto, and Vancouver, which is where I live. And I would encourage anybody who is thinking about starting a business using machine learning to consider having a software or a machine learning team in Canada, because not only are you getting pretty qualified people, but you're also getting a whopping bargain. Also, if you have a PhD and you think you might want to start a business, I would encourage you to look at an incubator in Montreal called Tandem Launch. And they take people who have science or engineering PhDs, and then they help them with the business side of things. So I know I have a science PhD and I don't really know anything about how to run a business. Well, these people will help you learn how to run the business. All right. The thought I would like to leave you with is, if you were to run a Kaggle competition, what problem would you propose? And if you're ever in Vancouver, come for a visit. Check out events at the Vancouver Learn Data Science Meetup. Thanks for your attention, and thanks for the Kaggle Days for having me here.